Hello and welcome friend. In this video we prove some theorems, some statement, some important results about congruences. In the previous video we have seen the definition and two important theorems on congruences. Here we will continue that and we will discuss in this video important result regarding the congruences. Congruence is a very important concept in mathematics. It is like an alternative to equality. Here this is a different way of presentation of an equality operations. You can see that on your screen I have written various different statement of the congruences. Whenever n is a fixed integer and a, b, c, d are arbitrary integers, then our first result is a congruences to a modulo n. Second result is if a congruences to b, then b is also congruences to a. Third one is if a congruences to b, b congruences to c, then a also congruences to c. Fourth one is if a congruences to b and c congruences to d, then we can add these two congruences and multiply these congruences and we will get a plus c congruences to b plus d modulo n and ac congruences to bd modulo n. If a congruences to b and c is any integer, then a plus c congruences to b plus c modulo n and ac congruences to bd modulo n. And our final statement is if a congruences to b modulo n, a raised to k congruences to b raised to k. Let us prove one by one. First result is very obvious. We know that we have a minus a equal to 0. We can write this 0 as 0 into n, and this implies that n is a divisor of a minus a and hence a congruences to a modulo n. This is a definition. If you remember the definition, a congruences to b modulo n, that means there exists an integer k such that a minus b equal to k into n, or n is a divisor of a minus b. If this definition is satisfied, then the function the two numbers a and b are said to be congruence modulo n. The first one is a very obvious, a minus a equal to 0, and we can write 0 into n. This guarantees that there exists an 0, therefore n is a divisor of a minus a, any integer 0, and hence n is a congruence to a modulo n. First one is very obvious. Now to prove the second one, it is given that if a congruences to b modulo n, then there exists integer k such that a minus b equal to k into n. Now multiplying by minus sign, we have b minus a equal to minus k into n. As k is an integer, minus k is also integer, so there exists an integer minus k such that b minus a equal to minus k into n, and hence b congruences to a modulo n. Third one, this is my first one, this is second. Now I am going to prove third. Let us apply. What is given? A congruences to b modulo n, and it is given that b congruences to c modulo n. Then by definition there exist integers k1 and k2 such that a minus b equal to k1 into n, and b minus c equal to k2 into n. Now a minus c equal to a minus b plus b minus c, but a minus b congruences to k1 into n and b minus c congruences to k2 into n. This implies that k1 plus k2 into n, and this gives us a congruences to c modulo n. Okay, this is a transitivity property of the modulus. Let us prove the fourth one. What is the fourth property? A congruences to b modulo n and c congruences to d modulo n. Then it is given if a congruences to b modulo n and c congruences to d modulo n. Therefore, there exist k1 and k2 such that a minus b equal to k1 into n, c minus d equal to k2 into n. Okay, this gives us, this is equal to, then a plus c equal to a plus c equal to let us add this. We can write this as a equal to, what we get here from this, a equal to b plus k1 into n and c equal to d plus k2 into n. Then a is b plus k1 into n plus c d plus k2 into n. This is equal to b into d plus k1 plus k2 into n. This implies that here b plus d, not a b d, b plus d, a plus c minus b plus d equal to k1 plus k2 into n. k1 and k2 are integers, therefore k1 plus k2 is again an integer, and this therefore a plus c congruences to b plus d modulo n, right? And AC into BC, let us take AC into A into C equal to what is A? B plus K1 into N. What is C? D plus K2 into N. Multiplication B into D plus B K2 N plus K1 N D plus K1 into K2 into N square. Okay, equal to B into D plus, taking N common, B into K2 plus K1 into D plus K1 into K2 into N into N. AC minus BD equal to K2B plus K1D plus K1 into K2 into N into N. So again K2 is integer, B is integer. This value gives us an integer. Therefore, this gives us that AC congruences to BC, BD modulo N. This is an important property to prove the fifth one, where we have to show that A plus C congruences to B plus C and AC congruences to BD. We can directly apply this property to prove the fifth property. It is given, what is given, that A congruences to B modulo N. We know that C congruences to C modulo N. This is by first property. Now apply the fourth property. This A plus C congruences to B plus C modulo N, and AC congruence is to BC modulo n. By fourth property, directly we can write these two. Okay, this is by fourth property. Now it's remain to prove the sixth property, and we will apply mathematical induction process to prove this result. If we take a, this k is equal to n, then for k is equal to n, k equal to 1, for k is equal to 1, a congruence is to b modulo n. It is given in the definition. Hence, the result is true for k equal to 1. Now, assume that it is true for k equal to m. That means a raised to m congruence is to b raised to m modulo n. This is my equation number 1. This is equation number 2. Both are true. Now apply the fourth property. Apply the fourth property. A raised to m into a congruence is to b raised to m into b from equation 1 and 2 modulo n. This implies that a raised to m plus 1 congruence is to b raised to m plus 1 modulo n. Therefore, the result is true. A result is true for m, for k plus 1, right? Then what we have shown, the result is true for k equal to 1. There is assuming that the result is true for k equal to m, we have shown that the result is true for k plus 1, and hence by mathematical induction the result is true for all values of k.